Hello, I am Akshat, a fifth-year PhD student at the University of Houston. I would like to begin by thanking the organizers of JMRA for this wonderful opportunity to present my most recent work on proving an Adelic version of the three-gap theorem, which has been done in collaboration with my thesis advisor, Dr. Alan Haynes. So I'll begin with recalling the classical version of the three-gap theorem. Then I will briefly introduce the setting in which we are working and then take a deep dive into our work. I will not venture too much into the details about the elements of our proof in an attempt to keep the talk under 30 minutes. All right, so first of all, let us consider a real number alpha and natural number n. Then we define psi k to be the fractional part of k alpha for all k ranging from 1 to capital N. Now we plot all the elements of the sequence psi k on the unit circle R mod z. What this will do is that it will divide the unit circle into n component arcs, and the length of each arc is the gap between two elements of the sequence. So we use delta kn to denote the kth gap, which is defined as the distance between psi k and its next neighbor to the right in this sequence. Little gn function is going to count the number of distinct gap lengths that we have. So the classical three-gap theorem, which is also known as the three-distance theorem or the Steinhaus conjecture, states that the upper bound for this little gn alpha function is 3. So the notations here are important. So because I'm going to use the same notations, which are xi and delta and little gn, for when we also define and state the result that we have. All right, so I'll give a nice illustration for this. So I'm taking alpha to be square root of 2 and n to be capital N to be 12. So we plot the points 0, fractional part of alpha, all the way up to fractional part of 12 alpha on the unit circle. So if you see, I'm going to zoom in a bit, the red length is denoting the first distinct gap length which you see, which is between 12 alpha and 0. The next distinct gap length is colored in blue. And for instance, you can see that between 5 alpha and 10 alpha, or 3 alpha and 8 alpha, and so on. And the third distinct gap length is colored in purple. And you can see that between, say, 8 alpha and alpha, or 11 alpha and 4 alpha. So there are 3 distinct gap lengths that we have in this particular illustration. And another important observation that we have is that if you consider the sum of the first 2 distinct gap lengths, then that gives you, so if you see this, it is going to be equal to the third gap length, which is colored in purple. So this additional statement that if there are indeed 3 distinct gap lengths, then the sum of the first 2 is going to be equal to the third gap length is also included a lot of times in the statement of the classical three-gap theorem. All right, so this is the classical version. Now I'm going to go ahead and start talking about the setting in which we're working. So first of all, let's consider a non-zero rational number. And for any particular prime p, we rewrite it in this form. So then with respect to this prime, the p-adic absolute value of this rational number a is defined to be p to the power of minus m. And by convention, for any prime p, the p-adic absolute value of 0 is just defined to be 0. Okay, so then we have the field of p-adic numbers, which is denoted by qp. And this is the completion of q with respect to the p-adic absolute value. And any particular p-adic number can be expressed in this series form, where all the xi's are going to be between 0 and p minus 1. Okay, So next, if we consider the particular p-adic numbers whose p-adic absolute value is less than equal to 1, then this gives us the ring of p-adic integers, which is denoted by ZP. All right. Next, we have the topological ring of the adeles, which is denoted by A. So any element in A is going to be this infinite tuple that we have, where the first component is a real number, and all the other places are indexed by all the primes. And for all but finitely many of these places, the p-adic numbers that we have should be p-adic integers. So it's important to note that this is a product over all the primes. And this has the restricted product topology. So this is the ring, topological ring of the adeles. Now, let's consider a particular set of primes P. So this is just a non-empty subset of the prime numbers. You're free to choose whatever you want. Then let's consider the another topological ring, which is denoted by AP. And this is the projection of the adeles specifically onto the places which are indexed by infinity, which is the real component, and then the primes which are occurring in the set P that we have. So this topological ring has the final topology with respect to this projection. Now, next we consider the additive group gamma P, and this can be diagonally embedded into AP using the injective homomorphism, which basically takes an element of gamma P, and then in each of the indexes, in each of the indices that we have from reals and the primes, it's just going to be gamma. So the same element is repeating on all the places. And with respect to this diagonal embedding, the image of gamma P can be identified with itself. And this is a discrete subgroup of AP. So now this gives us the machinery to go ahead and define the adelic torus, which is the quotient group AP mod gamma P. Okay, so this is a nice connected, compact, metrizable abelian group. And from a topological visualization point of view, if you consider the most basic form of the adelic torus, so for instance, if you have the set of primes the set of primes P to be just singleton 2, then the adelic torus that we have is this. And this most basic form of the adelic torus is actually homomorphic to the Smale-Williams solenoid. So that's just to have a topological visualization for the most basic form of the adelic torus. Okay, so as I said, this is a metrizable. So to move ahead, we need a metric. So what we do first is we define a metric on AP. So for that, it is again defined in two different cases. One where the set of primes is finite, and one where the set of primes is infinite. And for the case when it is finite, this is nothing but the maximum metric. And this is also the canonical choice of metric in the case when the set of primes is not finite. And with respect to this, AP indeed has the restricted product topology. And now we use this metric, which is defined on AP, to go ahead and define a metric on the adelic torus. And that is given in this form. So we are taking the minimum over all elements of gamma P. And this induces the quotient topology on the adelic torus. Okay, so this was just a brief introduction and preliminary details that we needed. Now I'm going to go ahead and first state the main result that we have. So again, I'm going to use some of the notations that I was using when I was stating the classical three-gap theorem. So first of all, we choose an alpha in AP and a natural number capital N. Then Sn alpha is going to be the collection of the fractional paths of little n times alpha, which we are denoting by xi n, as n runs from 1 to capital N. Now, for every little n, we have delta n and alpha, which denotes the distance of xi n from its nearest neighbor in the set Sn alpha. So we consider all the other elements of Sn alpha and then see which of the ones is closest to xi n, and that gives us delta n. Here, I would like to point out a small technical difference. When we talk about gaps, when we are talking about gaps in the classical version, that is going to be defined as the nearest distance to the right. So there's a particular direction in which you're going to look in when you're considering the nearest neighbor for any particular element k alpha. But here we are not doing that. We are just considering the nearest neighbor. But things still work out with us, but I just wanted to point out that technical detail. And so we define the little g and alpha function to be to count the number of distinct nearest neighbor distances that we have as n runs from 1 to capital N. So our version of the three distance theorem states that whatever choice of subset of prime numbers p you have, the little g and alpha function will always be less than equal to 3. So 3 is still the upper bound that we have. And then we also go on to show in the second part of our proof that this bound is best possible and it is definitely attained. Okay, so now I'll try to talk about just brief details of how we try and prove our main result. So the classical three-gap theorem has been proved a lot of times. It was first proved initially by independently by three people in the late 1950s, and since then it has been reproved a lot of times and generalized in many ways as well. One of the recent proof which we are interested in is given by Marklof and Strömbergsson in 2017. And they make use of the space of two-dimensional Euclidean lattices to give a proof for the classical three-gap theorem. So what we do is we take this approach of theirs to gaps problems in Diophantine approximation and use an adaptation of it to the adeles to prove our result. Okay, so that means that we need a space of lattices. So what we do is we take G to be SL2 AP and gamma to be SL2 gamma P. Then our space of lattices is G mod gamma, and this can be identified as the space of lattices of determinant 1 in AP squared. Okay, so our goal is to express the little g and alpha function in terms of a function on this space of lattices. So on the way, we also want to rewrite the nearest neighbor distance formula in terms of the space of lattices. So first, let's try to do that. And so if for some technical reasons, let's replace n with n plus half, which is denoted by n plus. So then this is our formula for the nearest neighbor distance. Now, taking m minus n to be k, we have this reformulation of the nearest neighbor distance with certain restrictions on k. So there is a lattice which is kind of hidden here in the background, and we want to identify what this lattice is. So in order to do that, let's consider any non-zero rational number t, and then define this lattice, which is given by t inverse t alpha 0 t. So we have already fixed the alpha in AP, and this is the lattice that we have. Then particularly for the case when t is n plus, we have an plus alpha. So we have an plus alpha, and let's consider any particular element in gamma p squared and left multiply an plus alpha with that element of gamma p squared. So the lattice vector that we end up having with this calculation is very interesting. So what I'm going to do is quickly try to copy this expression here. So the last expression that we had for the nearest neighbor distance. So this is what we have. And let me try to zoom in a bit. And you can observe that the second component of the lattice vector that we got from this calculation is very similar to the elements over which we are taking the minimum for getting the nearest neighbor distance. And the first component is actually very similar to the terms that you have in the restrictions for K. So, well, in our effort to get everything in terms of the space of lattices, we can use this calculation to rewrite the nearest neighbor distance. And what we do is we consider the lattice vectors, these particular lattice vectors, which are determined by the restrictions that we have on the first component. So if you see, this is the real component, and these are all the components of U in the places indexed by the primes P. So what we do is we use these restrictions to get a particular collection of lattice points. And this is basically giving you a particular strip in which you're going to see. Once you have this collection of lattice points, what you're going to do is take the absolute value of the second component and then take the minimum of that. And that is how you're redefining the nearest neighbor distance in terms of this lattice an plus alpha. But let's try to generalize things a bit, because it's dependent on an plus alpha. There's these particular restrictions here on how this strip should look like. So in general, for any lattice M and real number T between 0 and 1, we generalize the restrictions for the lattice vectors and define QMTZ that we have over here. And this is basically the collection of all the lattice vectors that satisfy these restrictions. So we have these restrictions on the first component, and this basically means that we are looking in a strip of length 1 between minus t and 1 minus t. So now this gives us a collection of lattice points. So we go ahead and define a function, capital F, which is going to look at all the lattice points that are there in this set QMTZ, and then take the minimum over the absolute values of the second component of these lattice vectors. So this is particularly a function on the space of lattices that we've taken. So this is what we're going to use to rewrite everything in terms of the space of lattices. But first, what we need to do is make sure that this function f is well defined. So for that, we used an Adelic version of the Minkowski's convex body theorem, which was independently developed by McFeet in 1971 and Bombieri and Waller in 1983. So using this theorem, we are able to prove that f is definitely well defined, which basically means that if we consider the set QMTZ for any t, there is going to be at least one lattice point that we have which satisfies these restrictions. Okay, so now this function f was defined for any general lattice M. So if we take the particular case where M is an plus alpha and t is n plus, then actually the nearest neighbor distance can be defined in terms of the function f. So this completes a very important step in our proof, where we have been able to write the nearest neighbor distance in terms of a function on the space of lattices. So now what we want to do is write the little g and alpha function in terms of the space of lattices. So for in regards to that, for any general lattice element M, let's define the function capital G, which is basically going to take or count the number of distinct values that the function f is going to take as t runs between 0 and 1. So basically, you have this strip of length 1, right, between minus t and 1 minus t. So you're going to keep moving it as t varies from 0 and 1, and you want to count the number of distinct values that the function f is going to take, and that is going to be the value of the function g. An important observation is that if you consider the specific case again, which is related to the little gn function, where M is particularly the lattice an plus alpha, then we have this relation, between the little g and alpha function, which is counting the number of distinct nearest neighbor distances, and the capital G function, which is counting the number of distinct values that the function f takes. So what this inequality does is that it reduces the problem of finding an upper bound for the number of distinct nearest neighbor distances to finding an upper bound for this function capital G. So hence, we, in order to prove our main result, we prove this more generalized result here, which is true for any lattice element M, that the upper bound for the function capital G is going to be 3. Okay, so this completes the reformulation of everything in terms of the space of lattices. So now I'm going to start talking about the first part of our proof, which comprises of trying to prove that 3 is definitely the upper bound. So first, let's take, so QMTZ was a collection of lattice points for a particular value of t. So QMZ is collection of all such lattice points as t runs from 0 to 1. Then the next important observation that we have is that for any lattice element M, this function capital G is actually finite. So since it is finite, let's go ahead and assume that the value of the capital G function is this natural number capital K. Then what this does is that it means that we can fix K different lattice vectors in QMZ. So let's denote those K distinct lattice vectors by U1, V1 going up to UK, VK. And what this means is that the function f is going to see these particular lattice elements, and the values that the distinct values that the function f is going to take are going to be V1 going up to absolute value of VK. Why is this? Because G was actually counting the number of distinct values that the function f takes. So these are, since it is equal to K, these are the distinct K values that the function f is going to take. We have some technical assumptions while we choose these lattice vectors in our paper. And they are basically meant to just ensure that we have the lattice vectors organized properly like this. And these are actually going to be the only lattice vectors that the function f is going to see. Okay, so now the next useful proposition that we have is that using the symmetry of the lattice space of lattice that we have, which is also useful in actually proving the well-definedness of the function f, and the way we are defining our collection of lattice points, if uv is in QMZ, then minus u minus v will also be in QMZ. So what this does is helps us in restricting to choosing only those lattice vectors, ui, vi, where the real component of the first component is going to be non-negative. So that's the freedom that we get with the last fact that we had. And both these facts are very, very important in the next few technical steps that we have in order to finish the proof. So since we assume that the capital G function is taking the value K, we basically want to prove that K is less than equal to 3. So we do this in 2 parts. First, let's take K1 to be the number of lattice vectors ui, vi, where the real component of the first component ui is less than half. So using the few facts that I just stated a few moments ago, we are able to prove that the upper bound for K1 is 1. So at most, we can have only one such lattice vector. Okay, so now the next thing that we do is define K2, which is nothing but the remaining lattice vectors for which the real component of the first component ui is between half and 1. So if K2 is less than equal to 2, then we are done, because K is K1 plus K2, and that gives us that 3 is the upper bound. So what happens if we have the scenario where K2 is 3 or bigger? So for that particular case, again, using some of the machinery that we use for proving the upper bound for K1 and some other technical details like the strong triangle inequality, we are able to prove that if that is a scenario, then the only possible case is that K2 is actually 3 and K1 is 0. So again, that means that the value of K is equal to 3. So this completes the proof that the upper bound for K is 3, which means the upper bound for the capital G function is 3. And using the inequality that we had, this also gives us an upper bound for the little g and alpha function, that there are at most 3 distinct nearest neighbor distances. Okay, so that finishes the first part of the proof. Now, to complete the proof, we also need to show that this is the best possible bound, and it is attained. So this was quite challenging because you can give any set of primes p that you like, so we have to be able to give you examples in any possible case that the bound 3 is attained. So we have 2 parent cases, which is kind of also dependent on the fact that how the metric is defined. So the first parent case is when the set of primes is finite, and this has 3 different subcases. The first subcase is that the set of primes is the singleton set 2. In that case, we take alpha to be this, and we take capital N to be 52. So then by computation, we are able to see that there are 3 distinct gap lengths, nearest neighbor distances that we have. So the little g and alpha function is actually equal to 3. The other 2 subcases in this are, the second one is that the set of primes p is singleton set 3. And the final one is that it is neither of the first 2. And for these 2 as well, we have other separate examples in our paper, but of course, I'm excluding those for the sake of time for now. All right, and finally, we have the other case where the set of primes could be anything, so it's infinite. So in that case, we are actually having to divide everything into 4 different subcases. The first one is where the prime 2 is contained in P, but 3 is not. The second is when the smallest prime in the set P is 3, so 2 is not there. The third one is that both 2 and 3 are there and other primes. So again, in our paper, we have distinct examples for all these 3 cases. And the fourth and final subcase in this one is when the smallest prime in the set P, which is being denoted by Q, is at least 5. So it will be 5 or bigger. In that case, the real component of our vector alpha is going to be defined as Q minus 1 over Q times Q minus 2. And the periodic number at the qth place is -1, and for all other places, it's just going to be 0. So that's our vector alpha. And we take capital N to be the smallest prime that we have, which is Q. So again, there are 3 distinct nearest neighbor distances that we end up having. Of course, all these values depend on whatever the smallest prime Q is. And this also gives us that G and alpha is equal to 3 in this scenario. So with all these different subcases, we cover any possible situation of what the set of primes P can be, and we give examples that the bound of 3 is actually attained, and hence it is best possible. And this finishes the second part of our proof. And so that concludes my talk. I hope this was a good listen for anyone who's here. And please let me know if you have any questions. Thank you so much again to the organizers of JMRA for giving me this wonderful opportunity to present my work. Thank you.